So you will need a graphing calculator handy for today's class. I have my TI-84 here. If you don't have a graphing calculator, you should be able to do this in GeoGebra or Desmos. We will just have to be a little bit creative with how we can get the exponential function for our data points. The other thing I want to mention is if you're taking a look at the calendar, the pacing of the calendar, we are not able to hold a live class for every single one of those lessons in the next upcoming week. So I was able to hold a live class on 3.01 and I'm able to do 3.02 today, but then next week how it falls is there's 3 lessons in the week that are due versus just 2. So because of that, I can only address 2 of those lessons, not all 3. So I do have a recording made for lesson 3.03. I will actually transfer that to YouTube for you and then post that in the content page. Once I have that embedded in the online content page for 3.03 in Canvas, I will email you guys to let you know. Right now I think I have it in there as just a Blackboard Collaborate recording, but since we're trying out this YouTube feature here, I'm going to post it on YouTube and you guys can watch it that way. So next week, the live classes will be on lessons 3.04 and 3.05. So if you're taking a look at lesson 3.03 and you're really kind of struggling with that, don't forget about the recording that I've made and we'll post for you. Any questions with that at all? Okay, then we are continuing on with our exponential and logistic modeling. So if you remember in Tuesday's class, we talked about exponential growth and exponential decay a little bit. I kind of alluded to that on how we can identify growth versus decay with our exponential formulas. We're going to expand on that idea today. So today we're actually going to find the growth and decay rate of an exponential model. So how fast is something growing or how fast is it decaying? So we're going to find that rate today. The formula that we use is very similar to your exponential formula or exponential function that you saw in 3.01. So in 3.01, remember they give you the formula y equals a times b to the x, where a was your initial value, b was your base, that's what you're multiplying by each time to get to the next term, and then x was that number of terms, so how long you were doing it for. You'll notice that the exponential population model function that they give you is very similar. The PO is going to be the same as the A that you had in your exponential function. It's your initial value, your starting amount, right? Usually that little subscript of O, when you see that, that is to signal your starting amount, your initial value of some sort. The next piece that's in parentheses correlates to the b that we had in our exponential function. That is your base. That's what you are growing or expanding by. Now, they wrote it as 1 plus r this time. And the reason they wrote that as 1 plus r is because r is referring to the rate you are increasing or decreasing by. So we can subtract that number from 1 and find how fast or slow we are growing. I kind of alluded to that a little bit in Tuesday's class as well. I kind of told you we could subtract from 1 to figure out the speed of growth. We're really going to look at that today. And then you'll notice the exponent is the same. So instead of x here, they just wrote t, because when we're looking at models, usually the variable that's present in model situations is in regards to time. So instead of having the variable of x, they use the variable of t. So t is in correlation to the time that it's taking place with. Now, when we look at the base here, what's inside the parentheses, the 1 plus r, if that value is larger than 1, you know that you have an exponential growth happening. If that value is less than 1, you know you have exponential decay that is occurring. Okay, so just some hints there for how you can identify growth versus decay. All right, before we look at some examples, any questions with that population model? Okay. Then let's go ahead and take a look at some examples here. It says, tell whether the population model is an exponential growth function or exponential decay. And once you've identified that, find the constant percentage rate of growth or decay. So basically, find the rate at which it's growing or find the rate at which it's decaying. So let's take a look at question A here. We have a population model for San Jose, and we need to figure out, is growth or decay occurring first of all. So taking a look at that, what is happening, growth or decay? What do you think? Tommy's saying growth. Isaiah says growth. I agree, growth. How did you know? Yeah, your base is greater than 0 or your rate is greater than 0 depending on how you're looking at that. Base is greater than 1, sorry, and your rate is greater than 0. So I like how we kind of put that all in there. Good. We are really interested in the base. What is this 800,000 number referring to? What is that 898,759 referring to? That's your starting population. Yep, good. So we're not really interested in your initial value, good, but that's your starting population. So we're looking at the base here of 1.0064. We have identified that this is a growth model. Now we just need to find the rate at which it is growing. So to do that, you take that 1.0064, subtract 1 from that, and you'll get 0.0064. 0.0064 is a decimal value. You do need to change that to a percentage still. So what is 0.0064 as our percent? Yeah, remember you've got to multiply by 100, which moves the decimal point 2 places to the right. So when they're asking for a growth rate or decay rate, they are looking for a percentage value. Okay. So we want the 0.64%. In part B, is this growth or decay? That is decay this time. Good. And now we got to figure out what the decay rate is going to be. It's a little bit different with the subtraction. So instead of subtracting 1, we're actually going to subtract this number from 1. So 1 minus 0.9858. And what does that give us? Oopsie. .0015 or 0.00142. It doesn't matter if you round here. I'm going to do is it 2 zeros or 1 0 in there? Okay. Now, if you would have subtracted 1 from this, that's okay. You would have gotten the same value. It just would have been negative. The negative sign is representing a decay that's occurring. We do need to change this to a percentage still. So no matter which way we're looking at it, how does that translate to a percent? a 1.42% for your decay rate. Now, you can leave it as a positive 1.42%, but if you leave it as a positive, you need to make note that this is a decay function. All right, if you don't have that it's a decay function, you must leave it as a negative 0.142%, because that then will identify that you have a decrease over time. Does that make sense to everybody? So you either need to have wording to explain that percent of decay, or you need to include the negative sign if you're not going to put the words of decay in there. Okay, these hopefully are review mostly for you at this point, I hope. We looked at some of these in Algebra 2. We didn't focus on growth and decay rate too much when we were looking at our exponential and logarithmic functions. But hopefully you've seen this maybe in a science class before, possibly in our Algebra 2 class. So it's not too difficult of a concept. All right, let's go ahead here and actually write an equation to represent the situation they're presenting. It says determine the exponential function that has an initial value of 12 and is increasing at a rate of 8% per year. So they're looking for the actual equation to represent this. So f of x or p of t, whatever you want that function to be, equals. How are we going to start this equation off? So if we're going to write the equation, how do we start it off? With your initial value. So, ooh, a telephone this time. So our t in parentheses must be telephone. Awesome. We do have to start with that telephone. Not the telephone. With the 12. There we go. Oh boy, it's going to be a long day for me, isn't it? Okay, so we're starting with the 12. And now we need to figure out what the base is going to be. How are we going to identify what the base should be here? Turn the 8% to a decimal and add 1. Perfect. I was a little worried that you weren't going to turn the 8% to a decimal at first, but we do need to do that. So 8% as a decimal is 0.08. And because this is growth, you are increasing, it is growth, you need to add that to the 1 that's inside parentheses. And technically, if I'm going to use t as my variable, I should come back and put t out here as well, just to stay consistent. So a 1.08 needs to be inside your parentheses there. That is the base at which you are growing by. Questions? Consistency is appreciated, that is for sure. Questions with that? Not too bad, right? Okay, how about this one? So this might be a question that you would see in like a science class of some sort. Nope, Isaiah, you can pop some ibuprofen though if you'd like and continue on with us. Nice try. All right, let's read the next setup here. Suppose a culture of 100 bacteria is put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will be 350,000. So this is a little bit more complicated in the sense that we actually have to solve a question here. It's not just setting up the equation. We do have to set up the equation, but then there's additional steps because we have to solve as well. So let's set up the equation. How are we going to start with that? So any ideas for me? Your initial value is 100. Good, and I think that's what Isaias was referring to as well. The initial value is 100. Does anybody know what the base is going to be? Two. Yeah, how did we get the 2? Tommy's right. It's going to be a 2. Yeah, doubling means that you are growing by 100%. So that's no problem, you guys. So doubling means you grow by 100%. So inside those parentheses for the base, you have 1 plus 1. And that's where the 2 comes from. We don't know how long, because it's asking predict when the number of bacteria will be 350,000. So we don't know the time that it's going to take to get there. We do know that the time is measured in hours, though. So that's something else we need to keep an eye on, is what they're presenting the time as, because we may have to do some adjusting to either the exponent or our final answer if it's asking for something in a different measurement. So if it's asking for days versus hours, we would have to manipulate our answer to reflect that. So we always want to pay attention to what that variable is represented as. So here, it's represented as in every hour. I do know that we are looking for our population to equal 350,000. So instead of putting P of T out here, I'm going to actually put that number of 350,000. All right, so there is the equation set up. How am I going to solve for T in that equation now? So here's where our Algebra 2 skills and Algebra 1 come into play. Tommy's right, we got to isolate the base because that's where the exponent is going to be located essentially. It's attached to the base. So we want to start off by dividing by 100. If I divide by 100, that brings that down to 3,500 equals 2 to the t power. All right, here's the kicker. What do we do at this point? How do I bring that variable down so it's not an exponent anymore? Yeah, awesome. Oh, I'm so excited. We have to use a logarithm here. Remember, the properties of our logarithms allow us to bring that down. Now, if you can't remember the properties of logarithms, I believe that they are coming up in lesson 3 or 4. So if you can't remember those right now, you're in luck. Those are coming up in the next lesson, so you'll have a good refresher there. All right, so if we do the log of both sides, so log of 3,500 here equals the log of 2 to the t power, we can bring the exponent out in front of that log. So we do have the properties that allow us to bring that down from the exponent and put it out front. All right, we are just multiplying on the right-hand side here. This is technically a multiplication sign, not a minus sign. So if that's multiplication, we can use division to move the log of 2. So we're going to divide by log of 2. You will need your calculator or a calculator that has the logarithmic functions on it. If you have a standard TI 83, 84, or 86 calculator, they all come equipped with that. I also believe that it's on the computer calculator if you're in Scientific View. So if you're in Scientific View, you should have a log button that you can use on there. As we are entering this in, log of 3,500 divided by log of 2. Make sure you're putting parentheses around those values of 3,500 and 2. And when you hit equals, it should give you the time. All right, I need to put units of measurement on this answer. So if I have 11.77, what's the units of measurement? hours. Yep. You could convert the 0.77 to figure out how many minutes that is, but we won't waste our time with that, seeing how I have kind of a lengthy problem coming up still. So 11.77 hours. All right, doesn't take too long for that bacteria to kind of explode there, but doesn't surprise us because that's what exponential growth is. Things get very big very quickly. Questions with that one? All right, let's do a little bit more practice with solving these logarithmic and exponential problems here. It says, suppose the half-life of a certain radioactive substance is 20 days, and there are 5 grams present initially. Find the time when there will be 1 gram of the substance remaining. So we need to first create the equation, and then we'll solve it. So what's the equation we can create here? A lot of information is kind of thrown at us. Start with your initial value of 5. Yep, always a good spot to start at. Let's figure out the base then. So is this growth or decay? First we should probably identify this. Growth or decay? Decay, because you're talking about half-life. Half-life means you are splitting it in half each time. So if we're talking about half-life, what's the base going to be? Yeah, 0.5, 1/2, right? It's half of what it was. Here's the kicker. Be careful with the exponent. It says we are talking about time, but the substance is decaying every 20 days. So we do need to incorporate this every 20 days into our exponent. So we're going to take the time and divide it by 20 because that's the cycle that it takes until for the next round to kind of kick in, right? So every 20 days. So we need to take the time and divide by 20 for the exponent. Now that's new. We haven't seen that yet, but I told you that we had to be careful of the exponent in some of these setups. This is where we have to be careful. Before I proceed on here, any questions with that t divided by 20? Okay, what do we want to set our equation equal to? So obviously this equation is representing the population. We're interested when the population equals 1. Good. Let's use our skills then to solve for t in this equation. So how are we going to start off? Yep, we start off by dividing by the initial value. So we're going to divide both sides by 5. As I do that, I am going to put my answers as decimals instead of fractions. So 1 divided by 5 is a 0.2. All right, because we've already done one similar to this, the steps are going to be the same, right? It's just that the values that we're seeing in the problem are changing. So if the steps are the same, what's the next thing we need to do to isolate the t? You need to take the log of both sides. Yep. That's the good news. You already have one of these kind of under your belt. So because of that, you know what steps are coming your way. As I take the log of both sides here, I'm also going to bring that variable down, or that exponent down. All right, I got to this point. I took the log of both sides. I dropped the exponent out in front of the log on the right-hand side there. What's my next step to isolating t? So now it turns back to algebra because log of 0.5 is just a constant. So using our algebra skills, how do we get the t by itself? Divide by log of 0.5. Yep. Log of 0.2 divided by log of 0.5 equals t over 20. We still have one last step. What are we going to do to get t by itself? Multiply by the 20. Yep, because if you're dividing by 20, you're going to multiply by that. All right, you do need a calculator in order to solve this though. So make sure as you're typing this into your calculator, and my batteries are low, go figure, you are doing so correctly. So 20 log of 0.2 divided by log of 0.5. There. Did everybody get their calculator to come up with the 46.44 technically? And I could do it a little bit faster than on my scientific calculator than you can if you had to use the computer one. So if you're using the computer one, it's probably a few more steps. Our units of measure looks like it's in days, right? So right here is the days. Okay, good. All right, awesome. Questions with that one? Okay, the next question is regarding some data tables here, and if we can create the exponential equation for this. We will come back to this one at the end. I want to take a look at one more problem here, and then we'll go back to the graphing calculator one and finish with that. All right, so we have a rumor model. This is probably one of the most popular examples of exponential growth that's out there. Everybody who talks about exponential growth has seen the rumor example. So this is a play off of that famous example. So it says, Watauga High School has 1,200 students in it. Bob, Carol, Ted, and Alice start a rumor which spreads logistically at that model given. Now, the variable that's in the model is representing days. So it's how many students who have heard the rumor by the end of day t. So how many students have heard the rumor by the end of day 0? So before the first day is even over with, how many students have heard the rumor? How are we going to figure that out? So by the end of day 0, what do we do? What do I do with that day 0? Substitute 0 in for t, yeah. So I'm going to go ahead and work on that. Let's simplify here. You're going to get e to the 0 power. What is e to the 0 power? 1, right? So technically you're going to have 39 times 1, which is just 39. So 1 plus 39 is 40. So then next we have to do 1,200 divided by 40. And that's going to give us how many students? 30. Okay, so by the end of day 0, 30 students have already heard this. Now, and day 0 means the very first day that they're starting it, right? So they're starting at 0. How long is it going to take for 1,000 students to hear the rumor? What are we going to do to figure that out? Set that equation equal to 1,000 and work backwards to solve for t. Now, when I set this up, this equation almost looks like a nightmare to solve, but it's not too bad when we break it down step by step. So it looks really bad at the start here, but don't panic. It's really not too challenging, which is the good news. Any ideas for me on how we might be able to work backwards here to solve for t? So if we brainstorm together, I think we can get there. Multiply by the denominator. Now, I'm not going to distribute when I multiply because I'm actually going to divide really fast after this. But I do want to multiply by the denominator so that I can eliminate the fraction in the problem. Eliminating fractions is always a nice thing because it makes the problem not as intimidating. All right, now I told you that I was not going to distribute because we're going to go right ahead and divide by the 1,000 on both sides right away. So I'm going to take this 1,000 over here and divide it. Well, 1,200 divided by 1,000 is just a number. It's just a constant. What does that simplify to? So to eliminate that fraction, let's put that as a decimal. That's just a 1.2. All right, because I don't have the 1,000, I no longer need my parentheses on the left-hand side here either. Okay, now the problem isn't quite as overwhelming, right? It looks similar to what we've kind of solved before. What's the next step we want to take to solving for t now? We don't want to take the natural log because we don't have e isolated yet. Once we have e isolated, then we'll worry about natural log. Yeah, so Rachel told me subtract the 1. That's exactly what I want to do first. I want to subtract this 1 from both sides. Okay, just to save myself some space, and I know that you guys are awesome with your math skills there, I'm going to erase that and make that just a +2. There's one more step you have to do before you can take natural log to get rid of the e. You must divide by the 39. All right, what is 0.2 divided by 39? That's going to be a decimal of some sort. Okay. Anybody verify Tommy's decimal before I erase this? Yes, Rachel can. Okay. 0.00 and his eyes. Thanks, guys. It's always good to have a backup before we start erasing things from the page. All right. So now let's go ahead and use Tommy's idea of getting rid of the e. So to get rid of the e, we have to use the natural log. We talked about that a little bit in Tuesday's class when we saw the natural base of e being presented. So we did mention natural log just a little bit there. Natural log will eliminate the e, and I'm left with just the negative 0.9t, because technically you can bring that exponent down in front. Natural log, you do have a button on the calculator for natural log as well, and my batteries are dying on my calculator. Go figure, right? So typing that in, 0.00513, you're going to get a decimal answer there. If you can leave the decimal answer as long as you can get it, you're going to have a more accurate response in the end. So what I would do if you're using your calculator to solve for t is leave that how it is and then just divide by the negative 0.9 right away. Okay, so don't technically round quite yet if you don't have to, and take that exact answer and divide by the negative 0.9. Then you can round the final answer in the very end if needed. So about 5.86, which means how long does it take for 1,000 students to hear the rumor? I would say almost at 6 days. So almost at the near end of 6 days, the rumor has reached 1,000 students, because 5.86 is almost 6 days. Near the end of day 6, 1,000 students have heard the rumor. Great. Questions with that at all? So really good just to kind of review our algebra skills there on how we can isolate the variable if it's up in an exponent. We will practice with that as we move forward in the unit as well. All right, let's backtrack to this population one, and I hope my calculator is going to hold out here because of the battery situation that's going on. We can actually find exponential regression using a graphing calculator. So if they just give you some data here, you can go ahead and figure out what the equation or that population model is going to be for the data using your calculator. So the first thing we have to do is put the lists in for the calculator to have the data, right? So to do that, remember we go, I think it's stat first. So hit stat, and I'll write this on the board. And then edit should already be highlighted, so hit enter. And those lists from last time are probably there. So we need to clear out the lists from last time. To do that, just use the arrow keys to go up to the very top of the list. Notice how my L2 is highlighted there. Hit clear, and then enter. And it's going to wipe everything out. Then do the same thing. Use the arrow keys to go over to list 1 and go to the very top where L1 is highlighted. Hit the clear button and enter. Okay, that got rid of everything, and now you can go ahead and put your new data in. Instead of using 1900, let's just use 0, 10. We'll use kind of these last two digits here for the x values. It's a little bit more practical that way if we go like that. When we get to 2000 though, if I'm just going off of the last two digits, what does the year 2000 technically represent? So if I'm going just by that, I can't use 0 again. How many years from 1900 is 2000? 100 years, right? So that data point has to start with the 100. How many years from 1900 is 2007? 107, right? So you need to use that as your X data point. All right, so go ahead, start entering these lists into your calculator. All right, when you have those lists entered, go ahead and give me a green check mark. I think it may be doable on GeoGebra. I just have to find where the exponential regression tool is in that program. I do think it's doable. I don't believe you'll actually need this for the homework assignment though. This is just kind of an extra piece in there. I think it is doable in GeoGebra. I just got to find where that function is. All right, let's hit second quit to get back to kind of your home screen. So second quit brings you back to the home screen. Your lists are in there. So to get the values for your exponential function, we've got to go to stat again. So stat. We need to go over to calc. Notice how calc is in the middle. So use the arrow key to move over. And it gives you a whole bunch of new options then. So once you're in that calc column in the stat key, we want to find number 10 in the list. So you got to actually scroll down quite a bit. It's going to look like EXPREG. So notice how mine says exponential regression. EXPREG. Find that button and hit enter. So in the calc list, find that EXPREG button and hit enter. It'll show EXPREG on your screen. Hit enter again. All right. It gave you values for A and B. Did everybody get the values of A is around 80.75 and B was around 1.0128, it looks like. A is your initial value, so it's a slightly off from what we started with there. But it is a regression line, which means it's not perfect. It's fitting a line to your data the best it can. So obviously the values it gives here might not be exact for the starting point, our initial point. Because our initial point looked like it was going to be at 76.2. But because this is a regression line, it's like the line of best fit almost for this data here. It's not going to lie perfectly with those points. It's saying that this is a growth model, that population is growing over time because my base is 1.0128. In fact, it has a growth rate of about 1.28%. So there's a lot we can kind of tell just based off this data. But you can, if you're given lists, you don't have to like do it all mentally. You can plug them into the calculator and use this feature to get the equation. All right, questions with that process? Okay, like I said, I don't think that you'll necessarily need this for your homework, which is why I saved this for the last. You will more likely need these type of topics for the homework, working backwards to solve for the variable in an exponent. All right, that's all I got for 3.02. Any major questions before I let you go today? All right, watch out for the 3.03 recording. I'll send an email out once I have that posted to YouTube so you guys can view that early next week. Because next week we'll only have time to talk about lessons 4 and 5 in the live classes. All right, I'll let you go though. Have a great rest of your week and weekend, and I'll see you all Tuesday morning. Bye, everyone.